Explanation: a proper graph coloring means giving every vertex a color such that any two vertices joined by an edge get different colors. Think of a school timetable. Each class is a vertex, and edge connects two classes that share a student, and the color is the exam slot. If two classes share a student, they cannot be scheduled at the same time, just as two adjacent vertices cannot share a color. Simple example: take a triangle, three vertices A, B, C, each connected to the other two. Because every vertex is adjacent to the other two, we need three different colors, say red for a, blue for B, and green for C. Any attempt to use only two colors will force at least one edge to join vertices of the same color, which is not allowed. Explanation: the chromatic number chi of G of a graph G is the smallest number of colors that can be used in a proper coloring of G. Formally, chi of G equals the minimum of K such that G can be colored properly with K colors. Step-by-step computation. Example 1, a path P4, vertices V sub 1 to V sub 2 to V sub 3 to V sub 4. 1 try K equals 1, impossible because there is an edge. 2 try K equals 2. Color V sub 1 red, then V sub 2 must be blue, V sub 3 red, V sub 4 blue. No adjacent vertices share a color, so 2 works. Hence chi of P4 equals 2. Step-by-step example 2, a 5-cycle C5, V sub 1 to V sub 2 to V sub 3 to V sub 4 to V sub 5 back to V sub 1. 1, K equals 2 fails because the odd cycle forces the first and last vertex to have the same color, which are adjacent. 2, K equals 3 works. Color V sub 1 red, V sub 2 blue, V sub 3 red, V sub 4 blue, V sub 5 green, all edges are proper. Thus chi of C5 equals 3. These two examples show the systematic trial of increasing K until a proper coloring is found, which is exactly what chi of G records. Greedy coloring algorithm colors the vertices one by one in a prescribed order. A procedure: choose an ordering V sub 1, V sub 2, V sub n of the vertices. For I equals 1 to n, assign to V sub I the smallest color starting at 1 that is not already used by any neighbor V sub j with j less than I. Why it always gives a proper coloring correctness. When a vertex V sub I is colored, all its already colored neighbors have colors different from each other by the induction hypothesis. The algorithm picks a color not used by any of those neighbors, so V sub I cannot clash with any previously colored vertex. Since later vertices are colored later, no future step can change the color of V sub I, hence the final coloring is proper. Limitation counterexample. Consider the bipartite graph K sub 2, 3, 2 vertices on the left, 3 on the right, each left vertex adjacent to every right vertex. Its chromatic number is 2 because it is bipartite. Order the vertices as the 3 right side vertices first, then the 2 left side vertices. Greedy colors the first right vertex red, the second blue, the third red since its neighbors are not colored yet. When we reach the first left vertex, both red and blue are used by its neighbors, so Greedy must use a third color, green. The second left vertex then needs a fourth color. Greedy uses 4 colors while the optimum is 2. This shows Greedy is not guaranteed to achieve chi of G. Clique number omega of G, the size of the largest complete subgraph called a clique. Because each vertex in a clique must receive a different color, omega of G is less than or equal to chi of G. Example: in K4, the complete graph on 4 vertices, we have omega equals 4 and indeed chi equals 4. Maximum degree delta of G, the largest number of edges incident to any vertex. A simple bound is chi of G is less than or equal to delta of G plus 1 by greedy coloring using any ordering. Example: in a cycle C5, delta equals 2, and the greedy guarantee gives at most 3 colors, which matches the true chi equals 3. Brooks' theorem: if G is connected, not a complete graph and not an odd cycle, then chi of G is less than or equal to delta of G. Demonstration: take a path P5. Here delta equals 2 and the graph is neither complete nor an odd cycle, so Brooks' theorem says chi is at most 2. Indeed, chi of P5 equals 2. For the odd cycle C5, delta equals 2 but chi equals 3. This one is an exception permitted by the theorem. These bounds are useful because omega of G is a lower bound that is often easy to see, while delta of G plus 1 and Brooks' theorem give quick upper bounds without a full coloring search. Four-color theorem, proved in 1976, states, every planar graph can be colored with at most 4 colors so that adjacent vertices receive different colors. In the language of maps, any flat map can be colored using only 4 colors so that no two touching regions share a color. Planar graph requiring 4 colors. The wheel graph W5 consists of a 5-cycle V1, V2, V3, V4, V5, V1 together with a central vertex C adjacent to all 5 outer vertices. W5 is planar. Draw the outer cycle as a pentagon and place C in the middle. Trying to color with only 3 colors fails. The outer 5 cycle itself needs 3 colors, but the central vertex is adjacent to all 3 colors, forcing a 4th color. Hence chi of W5 equals 4, showing the bound of 4 is tight. Thus the theorem guarantees that no planar graph will ever need more than 4 colors, but some do need exactly 4, as the wheel graph demonstrates. Explanation. The chromatic polynomial Pg of k counts how many proper colorings of graph G exist when exactly k colors are available, the colors being considered distinct. Deletion contraction recurrence for any edge E of G. Pg of k equals Pg minus E of k minus Pg slash E of k, where G minus E is the graph with E removed and G slash E is the graph with its 2 endpoints merged, contracted. The subtraction removes the colorings that become illegal after the contraction because the 2 endpoints would have the same color. Example, a path on 3 vertices pay 3. Vertices V1, V2, V3, edges E1 equals V1, V2, E2 equals V2, V3. Step 1, start with E1. Delete E1, resulting in 2 isolated vertices V1 and V2 together with the edge between V3 and V2 left. Contract E1, merging V1 and V2 into a single vertex U, leaving an edge between U and V3. Step 2, compute Pg minus E1 of k. The graph is a single edge between V2 and V3 plus isolated V1. Colorings equal k choices for V1 times k minus 1 for the edge, which is k squared times k minus 1. Pg slash E1 of k. The graph is a single edge between U and V3. Colorings equal k times k minus 1. Step 3, apply the recurrence. pp3 of k equals k squared times k minus 1 minus k times k minus 1, which simplifies to k times k minus 1 times k minus 1, equal to k times k minus 1 squared. Thus the polynomial pp3 of k equals k times k minus 1 squared tells us, for example, that with 3 colors there are 3 times 2 squared equals 12 proper colorings. The polynomial is a powerful tool because its degree equals the number of vertices, and its leading coefficient is 1. Find chi of G for a given small graph. Approach. Look for a large clique to get a lower bound, then try to color the graph with that many colors. If successful, the bound is tight. Sample, for a house-shaped graph, a square with a triangle on top, omega equals 3 the triangle. Color the square with 2 colors and reuse one of them for the triangle's base vertex, achieving 3 colors. Hence chi equals 3. Prove chi of G greater than or equal to k. Approach. Exhibit a subgraph that already needs k colors, usually a k clique, or argue that any proper coloring would force k distinct colors. For example, an odd cycle needs 3. Use the inequality omega of G less than or equal to chi of G. Apply Brooks' theorem. Approach. Compute delta of G. Check whether G is a complete graph or an odd cycle, the 2 exceptions. If not, conclude chi of G is less than or equal to delta of G. Combine with a lower bound to get the exact chi. Sample. For a connected graph with delta equals 4 that is not k5 and not an odd cycle, Brooks' theorem gives chi less than or equal to 4. If you also find a 4 clique, then chi equals 4. Compute the chromatic polynomial of a small graph. Approach. Use deletion contraction repeatedly until reaching simple graphs, isolated vertices, or single edges whose polynomials are known. Show a planar graph needs 4 colors. Approach. Present a planar graph containing a subgraph homeomorphic to the wheel W5 or K4 and argue that 3 colors are insufficient, usually by contradiction.